Welcome back, my structural analysis friends. Many different methods for solving for deflections of beams exist, and we've looked at several of the geometric methods already. The moment area method, the conjugate beam method, we've even done superposition. And all of those, while very useful, were somewhat limited in the complexity of the structure that you were able to analyze. They were limited mainly to beams. Okay, I'm going to show you a principle today known as the principle of virtual work, which is based off of physics energy calculations that is much more widely applicable and can be applied to a wide variety of different structures. So without further ado, let's get started. So we've been studying deflections, and as we mentioned in the intro, the two categories of deflection calculations typically fall into either geometric methods, which would be things like moment area, conjugate beam that we've talked about in previous videos, and energy methods, okay? And so this is the first foray into the energy methods calculation, all right? So we're going to deal with virtual work. I'm going to kind of walk you through the derivation today, kind of show you the idea. You've seen some of this when we were looking at kind of the basics and the foundations of moment area. Some of the concepts are the same, but the calculations are a little bit different. And so I'm going to walk you through the approach that's used for the method in this video, and then in the subsequent videos we'll get into more specific examples of applications to trusses and to beams and then to frame systems as well. Okay, so here we go. So we're going to define virtual work. You know, work from physics was basically equal to some force times the distance through which that force translates. Now, in our example, the way we're going to set this up is we're going to apply and have basically a cantilever beam with a couple of different loads applied to it. The one we're looking at here is a point load P acting out on the end of the beam, and we know that the beam will want to deflect downward, and that's this bottom deflected line. Now, there are a lot of little sublines that happen in here. Now, what happens is that every point along this beam, there is a moment that exists as a result of this applied load. So if we look at some arbitrary little piece, say here in the middle, we could determine the amount of the total moment that's applied on that little piece, because it's the moment that causes the flexing of the beam, which causes this displacement to occur. And so that moment we know will cause a rotation in the amount of, say, d theta. Okay, and then that can translate, if I look at the left end and the right end, like what we did with when we set up our tangential deviation derivations in moment area method, will account for some portion of the total deflection that is caused by the rotation of that guy right there. And then the next guy causes a little bit more, and the one after that causes a little bit more. And it's the sum of all of those little incremental displacements due to the behavior of each individual little element that add up to the total. And that's the basics for what we're going to look at. So again, our elastic curve is this bottom line, and then these other two dotted lines here are the boundaries of this element. Okay, now, if we look at kind of the definition of work back in physics, we said that an element subjected to work was equal to the load on that element multiplied by the displacement of that element. So it stands to reason that if this is the incremental equation for one of these guys, then I can total up all of the work that's being done by taking the integral then from delta to 0 of p d delta. Okay. And so this is for the work that's performed by the load P, because this load is moving through all of those displacements. There will be some issues that we'll have to get into when we start looking at displacements of loads at other locations and what work is being done by that as well. Sometimes they come along in what we call our free rider situation, and we'll talk about those in some of the subsequent lectures. Now, the basics of the physics behind this beam is that if we were to plot some sort of load versus deflection curve, even for a non-linear load application on this, as long as I have this curve defined, which is a plot of the load P versus the displacement that the member goes through on there, that the work is basically the area under this curve. And you can see that from this equation. We're integrating P and then d delta. Okay, so we're integrating this P function, if you will, that this function P is some function of delta, which is kind of backwards of thinking about it, but the premise is still there. Okay, but our idea is that this shaded region represents the work that this beam goes through due to load P as it moves through its displacement of delta. Okay, All right, so here's what we're going to do. Now, there are a couple of things that we need to look at. Okay, is that for a linear behavior case, which is one of the assumptions we've been making all along about linear, elastic, isotropic, homogeneous, the linear cases fall into two different categories. The first one, if I plot P delta, a linear gradually increasing starts at 0 and builds up to some amount delta for the work energy that's being performed. And you can see that if we go back to our idea that work is the area underneath this curve, for a gradually loaded beam, the work is going to be equal to 1/2 of P delta, because we've made a triangle here, as opposed to, say, a linear load in which it's an instantaneously applied. There is no gradual buildup. It just hits and it's there. Okay, in that case, this is my P delta curve on this. And you can see that now for instantaneously applied loads, it's now P delta. Okay, and so that's what we're going to be looking at. So for cases where delta is caused by load other than load P, then this is the case that we would be using, that the load is already there, and then it would be kind of a free rider situation. So we'll be taking advantage of both of these guys. Now, for moments, this is all fine and dandy if we have point loads, but what if we have moments? Well, there's another variation of this formula where we had the work increment is P times d delta. The work increment due to a moment is m times d theta. Okay, and so d theta then was the amount of the rotation associated with just that one little element. Okay, so we have both on here because beams are loaded with concentrated forces and they can be loaded with moments as well. Okay, and so using the same kind of premise of our principle of work here, I can say that work is now the integral from theta to 0 of m d theta. Okay, and likewise what we had with the diagrams for the gradually loaded and instantaneously loaded, a gradually loaded moment is 1/2 m theta, and a kind of a free rider or instantaneous load is m times theta. Okay, all right, so that's kind of the basics of where we're going to this. Okay, so let's talk about the principle of virtual work. Okay, so this was introduced by John Bernoulli around 1717. So this one's been around for a while. It was some mathematicians that were working on all of this. And basically what it does is it divides a beam into two areas. Okay, we have rigid bodies and we have deformable bodies. Okay, for rigid bodies, the principle is that if a rigid body is in equilibrium under a system of forces, and if it is subjected to any small virtual rigid body displacement, the virtual work done by the external forces is 0. Okay, so that's kind of our basic principle, that if it's in equilibrium, nothing is moving, nothing is displacing, then there should be no work done. Okay, now what we're going to do is we're going to define, basically that the definition of virtual then is basically it's going to be an imaginary or a non-real displacement. So we're going to create a system, a virtual system, and then we're going to calibrate it back to what the real system is doing. Okay, and we'll kind of show you what we mean by that. And so the basic derivation looks something like this. Let's take a simply supported beam with a point load P acting at some angle. Okay, it's applied at a distance A from the left end. That's our usual nomenclature. L is the span on this. That the free body diagram of this beam looks something like the following, that we have an AX and a Y reaction because it was the support reactions. We have a CY, which is my support reaction here. And then I have components of this force P that I will call PX and PY. Right. Now, this doesn't have any concentrated moments on it. We're just looking at loads and displacements for what happens there. Now, if we look at the behavior of a rigid body in space due to all of these loads, we can see a couple of things. Okay, so we're going to allow, suppose that a small rigid body displacement is applied such that we can move our beam A, B, C to some new location. Okay, that the definition of what would happen if this beam were to move, translate, that basically, and rotate at the same time, if this is the original position, an arbitrary location would be that A prime goes to here, C prime goes to here, and B prime goes to here. It's still a straight line for a rigid object. That there are all sorts of displacements that have now developed as a result of this just generic definition of rigid body displacement. Okay, and it does include rotation and translation. And so if we look then, the total work that's done, we not only have work that's being done in the X direction by the X forces, but we have work that's being done by the Y forces in the Y direction, and we also get this rotational effect which is a function of the amount that it rotates, or this angle theta that we have here. Okay, now, the way that we're going to define this, we're going to come back to a lot of these values, and let's take a look. So A is going to move horizontally to A prime by a distance of what we call delta Vx. And A is going to move vertically to A prime by an amount delta Vy. Okay, and if I apply those translations, I would have a beam that is horizontal centered at A prime. But we know that we also get a rotation where this thing is trying to rotate that way as well. And so we have to come up and figure out, well, how much did point B, so if I look at this dotted line, this is where the B would be and the C would be out here somewhere. Okay, but now we also get extra displacement as a result of the rotation that is going to affect these loads for, say, B prime. And so if it's a distance of A from A to B, a little a that is, then the amount that B prime moves up is also A times the angle theta V, and where the theta V is the angle that's here. Okay, and then likewise, the height that C moves through is then going to be L times theta V, because it's the full length of the beam multiplied by the angle. And again, we're assuming small displacements, so I don't have to worry about any tangents or sines showing up. We're just using some basic relationships for that. Okay, and so if we look at that, then if we are willing to recognize that there is work being done by all three of these different components, then the total work is going to be equal to then WVX, WVY, and W due to the rotation all added together. Okay, so again, we're piling up energy. They don't have signs. It's just magnitudes or quantities happening there. All right, so then if we go through and we write out our equations, we can see from our picture on here then that the work done in the x direction is going to be AX times delta Vx, okay, minus PX times delta, the work being done by the virtual system. Okay, and so if you look, then what happens is that obviously AX we assume to the right, PX we assume to the left. That's why there's a minus sign. And I can do a little bit of algebra, and you can see that I get an AX minus a PX times that, whatever that displacement amount was. Okay, and if I factor this out, then AX minus PX is simply the sum of the forces in the x direction multiplied by whatever that displacement is. Now, I don't know this guy, but I do know him. Okay, so that's kind of cool. So we'll keep that in mind. And we can do the same thing for the y direction. Y direction is a little bit more complex because I get the rigid body stuff, which is AY delta Vy minus PY delta Vy. Okay, but I also get the force Cy that has now moved through delta Vy. And then I get this difference amount of AY, PY, and CY all multiplied by delta Vy. Okay, and so that would be the amount through which everything is basically moving for the rigid body displacement here. And just like before, if I factor all this stuff out, I get sum of forces in the y multiplied by that displacement is my basic derivation. Okay, so that's good. Now, what happens with the rotation? So the rotation is a little bit different, okay? The work being done by the rotation then is equal to the loads that we have on the system in all of these places. Now, we have a px and a py, and as well as our delta terms, that the incremental that's happening on this, if we go back and look at our basic picture, that the py guy here, we've accounted for the rigid body displacement to get him up to this line, but there's also an amount, because py is acting at b, of a times theta v, this additional amount that we have to add that's caused by the rotation. And likewise, the cy for the point that was here has to go through this L times theta distance amount for the extra work that's being done as well. We've already accounted for this guy. That's the rigid body displacement that we have happening there. All right, so if I write this equation, then what do we get? We get minus py times a theta v plus cy times L theta v. And then if I simplify this down a little bit, I get minus a p in y component plus L times c y component. Okay, and all of that multiplied by the angle through which it rotates. And if you look at these guys, those amount to the sum of the moments about A. Okay, it's A times the vertical distance and CY times the length of the beam. That's sum of the moments. So it's you're kind of seeing the same pattern, and then all of that gets rotated by that virtual rotation. So the external work that's being done on this system is the sum of forces in the x times the rigid body displacement in the x plus the sum of forces y times the rigid body displacement in y plus the sum of the moments times the rigid body rotation on that. Okay, now we talked about the physics principle. If the beam is in equilibrium, what do we know? Well, we know that the sum of forces x is 0, we know the sum of forces y is 0, and we know the sum of moments is 0. Okay, those are Newton's laws. And if all of those are 0, then this equation tells me that the virtual external work is equal to 0. Okay, so the external work value is a 0 value when the beam is in equilibrium. Okay. All right, now that's what happens for rigid bodies. For deformable bodies, it's kind of the same process, but it's a little bit more involved. So let's talk a little bit about what we're going to look here. If a deformable structure is in equilibrium under a virtual system of forces or couples, and it is subjected to any small real deformation consistent with the support and continuity conditions of the structure, then the external work done by the virtual external forces and couples acting through the real external displacements is equal to the virtual internal work done by the virtual forces acting through the real displacements. So we're going to kind of calibrate two different systems. I'm going to take a real system and apply a virtual displacement that will be the same as a virtual system going through a real displacement. Okay, and it kind of maps out this way. So what we've got is we've got a deformable body here in which I have two members that are connected at a point. Okay, and then I apply a horizontal load, that we'll say is some virtual load PV. Well, if this deforms, then this point is going to move in the direction of the load. Okay, and we're going to call that then as a delta. And this is a small real displacement due to a virtual load P. This is what the structure would see. We have an angle theta 2 made with the horizontal for this member and an angle theta 1 for this member. But you'll notice that that was from the original point. When I get out to this new deformed location, that angle has changed because now the distance is longer from, horizontally speaking, that it has to change the angle of here. Okay. Now, so what happens is that the forces in these objects become a function of their displacements. In fact, for this guy, that's exactly what we're seeing. Okay, and so we can come up with a little bit of math to figure out, well, the force in member BC, if you will, due to this virtual load force F here, it would be this guy. And it's a function of the angles of the thetas that we've created. Okay, and then likewise the force in this member as well. Okay, and yet there's this distance that this virtual force has moved through. That will be the virtual work that we're kind of looking at. So all we have to do is now figure out, well, okay, well, if this is my external stuff, we can find that, okay, but what can we do with this guy? And that's the trick, and that's where the power of the method is going to start to show up. Okay. All right, so if we kind of go through and we do our math on this, kind of the same derivation on this. If we do sum of forces in the x, okay, we get our PV minus our FVAC cosine theta 1. That's the horizontal component of this guy. And then minus FVBC cosine theta 2 all have to be 0. And then sum of forces in the y, we do the same thing for the y components of these two guys. So FVAC is negative sine theta 1, okay, because it's acting down. And then the virtual BC times sine theta 2 is acting up, so it's a positive. It's all equals to 0. Okay, now if we look at the total virtual work then that's done on this, it's then going to be, the virtual work is going to be PV times delta minus FVAC times delta cosine theta 1 minus FVBC times delta cosine theta 2. Because back on that picture that we had, that we showed you here, all right, the amount of displacement that this guy goes through, and again, we're looking at a force that's on an angle, that if this is delta, then this is delta cosine theta 1. And likewise, if this is delta, then this is delta times cosine theta 2. Okay, and that will be the work that this guy goes through, and that will be the work that, and the other one is the work that this one goes through. So we've got to get all of them on there onto this free body diagram for this member. All right, and so that's what we were doing, and that's where these cosine theta delta terms are coming in on there. And so if we kind of work our way through all of this, we get, and we can kind of factor some things out. Delta is common to everything, so PV minus FVAC cosine theta 1 minus FVBC times cosine theta 2. All of that multiplied by delta, well, just like we saw before, this is the sum of the forces in the x direction. Okay, and for equilibrium, we're going to set it equal to 0. If it's not in equilibrium, meaning that something is allowed to deform, then that term goes away. Okay, but if we're going to force equilibrium on this, then the virtual work equal to 0 tells me then that if we rearrange this, that our PV times delta, which was our external work, is going to be equal to then the virtual AC times its displacement, and the virtual BC times its displacement is the internal stuff, because this force and this force were internal forces, and this one were external. Okay, and so what boils down out of all of this is that the idea that we can calculate this external work as being the applied loads, that the work from the external, okay, what we call virtual external work, VE, is going to have to be matched by the work that's being done internal. Basically, exterior work is matched by the internal work. And all we're going to do now is then, when we get into our new methods, is come up with ways to calculate these different work quantities. So the internal work is going to be a function of the stress and strain that the member goes through, which is a function of the material properties and its geometry. And the external work is a function of the loads and where they are applied on the structure. And we've just showed that we can set these two guys equal to each other for this, and that our virtual external work is equal to the virtual internal work. And this is the basis of what we have happening. Now I know it's a lot of derivation in theory, but hopefully the samples are clear enough. In the next video, we'll start applying this to actual structural systems and come up with how do we calculate this WVI, because that's the trick. Okay, and so for trusses, you do it one way. For beams, you do it another. For frames, you do it another. For torsion, it's another. But the virtual external work is always the same, okay, based on the external loads and the deformations through which the body is going. So anyway, I hope the basics made some sense. I'm sorry there aren't any real examples here. It's more of a derivation, but trying to explain the premises. Stay tuned for the next videos where we'll get into some actual computations and some actual examples. But this is the theory that sets us up for what we're going to be doing in the next 4 or 5 videos as far as virtual work goes. It's a very powerful method, and so we'll take advantage of the tools that it affords us. So if you've got any comments, please be sure to leave those down below for us. We'll always get back to you on those. If you got any questions or concerns, please let us know. And then as always, if you found the video useful, please toss us a like, and then be sure to subscribe to the channel, and that will let you know when these other videos show up. So we'll see you guys next time. Happy engineering.